In this lecture, we take a look at two basic problems involving the use of work energy theorem. They are both simple horizontal situations that we could have examined in our previous unit on dynamics. However, when you use F equals ma as your starting point in analyzing a situation, it says nothing at all about energy transfer. So then therefore, we're going to get a deeper understanding as to what is happening in these two examples by using the work energy theorem, and we'll understand the energy transfers that occur. So there are two examples. Let's go ahead and take a look at the first one. Please copy it down into your notes as I read it to you here. Okay, a box of mass 1 kilogram is initially at rest on a horizontal frictionless surface. A horizontal force of 20 newtons is applied. Use the work energy theorem to calculate the speed of the box after it has been pulled for a distance of 3 meters. So all that's going to happen here is I'm going to take my eraser, for example. We'll consider this to be a horizontal frictionless surface, and then I just do the following. Like so. And then the problem ends the instant that I let go of the eraser. The eraser will have some speed when I do. We'll consider once again the desk to be horizontal and frictionless. Okay, so let's go ahead and draw out the situation. Okay, here's this horizontal surface, and here's our object of mass m. The mass is given to us as 1 kilogram to keep the numbers easy, and the object begins at rest. Okay, and then I come along and I apply a horizontal force of 20 newtons. We'll call this F pull, just to give it a name. So right here, like so, is F pull equal to 20 newtons. Okay, and then I pull the object over a distance, so that's the displacement here in this problem, of 3 meters. So right here, for example, delta r, this is equal to 3 meters. And then when I let go of the eraser, I do so right here at this point, and the eraser then has some speed v. Okay, now even though I'm not going to use F equals ma to solve this problem, I'm instead going to use the work energy theorem. Let's still draw out a force diagram so we can see the relationship between the force vectors and the displacement vector. So then therefore, as I pull the object to the right-hand side here horizontally, and there's no friction, we only have 3 forces acting on the object. We have, first of all, vertically, the normal force and the object's weight, mg. They just cancel each other out. Okay, and then we have F pull here to the right-hand side in the same direction as the displacement vector, delta r. And now here's then what we write for the work energy theorem. Net work equals change in kinetic energy. Always begin by filling in the right-hand side of the expression first. The right-hand side of the expression is always the same thing in the following sense. It's the final value of kinetic energy, 1/2 mv squared, minus the initial value of kinetic energy, 1/2 mv naught squared. In this particular case, the final kinetic energy will be based upon the unknown speed v, like so. And then we subtract from that the initial kinetic energy, which is 0, because in this situation, the object begins at rest. Like so. And then the left-hand side of the expression is the work calculations that we did in an earlier lecture. What we do is we calculate the work done by each force, and then we add all of those work calculations together to get the net work done. So let's take a look at, first of all, the work done by the normal force. Okay, now notice that the normal force vector is perpendicular to the displacement vector. So because those two vectors are perpendicular to each other, the normal force does no work. So the work done by the normal force is equal to 0. What this means is that the surface itself does not transfer energy to or remove energy from the object. If the work done by a force is equal to 0, that force does not transfer energy. Recall that the role of work, the reason why we define it, is to transfer energy. It's a mathematical representation of it. Therefore, if no work is done by a force, no energy is transferred. Same thing for gravity in this horizontal situation. No work is done by gravity because the gravitational force vector is perpendicular to the displacement vector. Let me write that here as well. So the work done by gravity is equal to 0. Therefore, the left-hand side of the expression here is only going to be one thing. It's going to be the work done by F pull. So let's go ahead and do that calculation next. Okay, I'll do that right here. Okay, the work done by F pull is equal to force times distance. It's equal to F pull multiplied by delta r. The reason for that is because the force vector here is in the same direction as the displacement vector. Therefore, force times distance is a positive value. That positive value, F pull times delta R, that goes right here now in the work energy theorem. So you add together the work done by the individual forces to get the net work done. Now, before I go ahead and manipulate this algebraically to solve for the speed v, because this right here is a positive number, what that then means is that that force, F pull, transfers energy to the object. Recall in the earlier lecture that we periodically wrote down a couple of questions in your notes. One of those questions was, what does it mean when positive work is done? What that means is that this force transfers energy to the object. Let's write that out. This force transfers energy to the object. Okay, now here on the lower board, I'm going to just go ahead and rewrite this expression. I'm going to throw away this 0 when I do. Okay, so on the left-hand side, we have the work done by F pull. That then equals the right-hand side, which is the kinetic energy. This expression right here is an expression of the energy transfer that occurs. Understanding the energy transfer is the most important part of this problem. Think of energy transfer as what form of energy becomes what other form of energy. Here's how you can begin to think of it. Now, this right here is the work that is done by the external agent, the work that is done by me. This is then therefore equal to the energy that I use. The energy that I use to do this work, that then becomes the kinetic energy of the eraser when I let go of it. So think of it this way, this becomes this. So this right here is the energy used by me. We just generically say the energy used by an external agent. And that then becomes the kinetic energy of the object. Now, if we used F equals ma in kinematics to describe a problem such as this, it would have said nothing at all about energy transfer. So we're getting a deeper understanding as to what is happening here physically in a problem such as this by using the work energy theorem. Okay, now let's go ahead and do the math here and then solve for the speed v. So I'm going to erase some of the words here. Make sure, of course, that you do have these words written in your notes, like so. Okay, and now I'm going to go ahead and take this expression here and solve it for the speed v. So first thing to do is cross multiply the 2 and divide the m to the other side like so. So I'm doing here the algebraic steps for us to get v squared by itself. And now we just take the square root of both sides. When we do, we end up with a positive number, we end up with a speed. Like so. Okay, and now I can go ahead and plug in my numbers. So we have here, first of all, 2 divided by 1 kilogram, so just 2, and then multiplied by 20 newtons, and then multiplied by 3 meters. Take the square root of all of that. So I'll go ahead and plug in my numbers now in my calculator. So 2 times 20 for the force, and then multiply by 3 meters. Take the square root of all of that, and it comes out to be a speed of about 10.95 or so meters per second. Once again, we could have done this problem by using F equals ma and some kinematics. However, by using the work energy theorem, we get a deeper understanding as to what is happening physically in the example. Okay, now in this example, the object was speeding up, and the net work done was a positive number. Let's now, in the second example, see what happens when an object slows down instead, and it will slow down due to friction. Now I'm going to go ahead and erase the boards. Like so. And now let's take a look at the second example. Let me put it on my screen. Okay, I'm going to use my eraser to demonstrate this. The problem says, an eraser with a mass of 0.1 kilograms has an initial speed of 3 meters per second as it comes to rest on a horizontal surface. A force of friction equal to 1/3 of the object's weight opposes the motion. Calculate how far the eraser slides, and will ultimately also describe the energy transfers that occur. So basically the problem looks like this. Now the problem begins the instant that I let go of the eraser, and the problem ends when it comes to rest, like so. So in other words, when I let go of the eraser, that's when I give it its initial speed of 3 meters per second. We'll then calculate how far the eraser slides in coming to rest, okay? So once again, the problem begins the instant that I let go of the eraser. So now let's set up the scenario. All right, so here's this surface. Here's the eraser of mass m equal to 0.1 kilogram, and it's initially moving to the right after I let go of it with a speed of 3 meters per second. Okay, it ends up at rest over here. Its final speed is equal to 0. And then, I'll use another color. Right here is the unknown. Right here is the displacement vector delta r. This is the distance that the eraser slides in coming to rest. Okay, now let's draw out a force diagram. Once again, the problem is only referring to what happens after I let go of the eraser. So after I let go of the eraser, I am no longer exerting a force upon it. Therefore, the force diagram after I let go of the eraser looks like this. So we once again have the normal force here and the weight just canceling each other out. And then opposing the motion like so is the force of friction. The motion, the displacement vector, is to the right-hand side. Now we're given that the force of friction is 1/3 of the object's weight. And then once again, we analyze the problem by using the work energy theorem. Okay, so net work done equals change in kinetic energy. The right-hand side of the expression in this problem is backwards of what it was in the previous example. Remember that the right-hand side of the expression is always the same thing in the following sense. It's the final value of kinetic energy, in this case that's going to be 0, minus the initial value of the kinetic energy, where the speed is v0. So we write then the right-hand side of the expression as the final minus initial kinetic energy, like so. Notice the negative sign there, because the final value of the kinetic energy is 0, the eraser ends up at rest, and the initial value depends upon the speed v0. And then the left-hand side of the expression is, once again, the net work done, so we calculate the work done by the individual forces and add it all together to get the net work. Okay, once again in this example, however, like in the last example, no work is done by the normal force, no work is done by gravity. Both of these force vectors here are perpendicular to the displacement vector delta r. Therefore, the only force that I do have to worry about is the force of friction. Notice that the force of friction points in the opposite direction of the displacement vector delta r. Therefore, when you calculate the work done by that force, it's a negative number. So then therefore, the left-hand side of the work energy theorem is once again force times distance, but in this case, it's a negative number because the force vector associated with friction is opposite of the displacement. Okay, now let me go to the lower board here and kind of rewrite the expression. I'm going to get rid of this 0, of course, and then notice that the negative signs will cancel out. Before I do that, however, one more thing about this work calculation for the work done by friction. It's a negative number. We now know what that negative sign means. It means the following in terms of energy transfer. This force, the force of friction, removes energy from the object. Let's go ahead and write that here. This force removes energy from the object. Okay, incidentally, by the way, before I do the remainder of the example and just solve for the displacement, if the force of friction is removing energy from the eraser, for example, after I let go of it like so, what happened to that energy? Well, it actually becomes another form of kinetic energy. This is referred to as heat. It's the kinetic energy of the molecules that make up a substance. For example, as the eraser slides over the desk, the moving eraser is doing work on some of the atoms and molecules that make up the surface of the desk. After the eraser slides over the desk, the molecules and atoms that make up the surface are vibrating in place with a little bit more kinetic energy than they had prior to the eraser sliding across the desk. If we had a sensitive enough thermometer, we would actually detect that the temperature of the desk after the eraser slides over it is a little greater than prior to the eraser sliding. And the reason for that is because the kinetic energy of the eraser after I let go of it is becoming another form of kinetic energy, and this is referred to as heat. It's the kinetic energy of the molecules of a substance, in this case the molecules and atoms, for example, that make up the surface of the desk. Okay, now let's go ahead and finish the example. I'll jump to the lower board to do so. I'm going to cancel out the negative sign here and here. I'm going to get rid of the 0. So that then gives us this. And then once again, think of this statement right here as a statement of the energy transfer, and qualitatively, this is the most important part of the problem. Once again, think of the energy transfer as a statement of what form of energy becomes another form of energy. In this case, the energy transfer happens this way in my expression. This right here is the initial kinetic energy that I give the eraser when I let go of it. And then that initial kinetic energy becomes this. This is the heat that is transferred to the desk below. Heat transferred to the surface. Like so. Once again, if we had set up this problem by using F equals ma and some kinematics, we could ultimately do the problem, but it wouldn't say anything at all about the energy transfer that occurs. So with the work energy theorem, we once again get a deeper understanding as to what is happening physically in the situation. Okay, now I'm going to erase the words here, and then let's just go ahead and finish the problem. Make sure, of course, that you have this information in your notes. Okay, and now in order to finish the problem, let me make this 2 a little bit more clear, like so. Let's plug in what we're given about the force of friction. Up on the top board, the force of friction was 1/3 of the object's weight. So let's go ahead and plug that in. Like so. Okay, now in doing so, notice that the mass of the object actually cancels from the expression. Like so. And now what we're going to do is solve for the displacement delta r algebraically. I'm going to move the 3 over here to the right-hand side of the expression, and then take the g and move it down to the denominator on the right-hand side. So the displacement delta r is then therefore equal to the following. First of all, 3 times v0 squared, like so, and then divided by 2 times g. Like so. Let's go ahead now and plug in our values. When we do, we end up with a distance in terms of meters. All right, so let's see. I've got 3 times v0 squared. So v0 was 3 meters per second. So 3 times 3 squared. So that's a total of 27. And then divide by 2 times g. So 2 times 9.8. And this ends up being about 1.38 or so meters. Like so. Okay? All right, we won't go any further than that involving the work energy theorem. Just 2 horizontal situations. In the first situation, the object was speeding up and kinetic energy was being gained by the object. I was transferring energy to the object, for example, in that problem. And then here in this second example with the object slowing down, the kinetic energy is being removed by friction, and it's ultimately being transferred to the desk below as heat.